Electricity is built into almost every gas appliance, from ignition to blowers to safety controls. If you want to pass Module 5, you need to understand not just what electricity is, but how it moves, what makes it move, what stops it, and how that energy gets turned into heat, light, magnetism, and motion. This chapter starts at the atom and builds all the way to circuits, meters, motors, transformers, code, and safety. Everything begins with the atom. Matter is made of molecules, and molecules are made of atoms. There are more than 103 elements, and each one has its own atomic structure. At the center of the atom is the nucleus, containing protons and neutrons. Orbiting the nucleus are electrons. Protons carry a positive charge, electrons carry a negative charge, and neutrons carry no charge. In a balanced atom, the number of protons and electrons is equal. Copper, for example, has 29 protons, so its atomic number is 29. The energy involved in the movement of electrons around the nucleus is electrical energy. Opposite charges attract and like charges repel. That rule explains a huge part of electricity. Electrons are held near the nucleus by attraction to protons, but electrons in the outer orbit, called the valence shell, are held more loosely. The outer shell can contain a maximum of 8 electrons. Good conductors such as copper, silver, and gold usually have only one valence electron, so that outer electron can move more easily. Oxygen has 6 valence electrons and is a poor conductor. If an atom gains extra electrons, it becomes a negative ion. If it loses electrons, it becomes a positive ion. A charged body can repel like charges, attract opposite charges, conduct its charge to another body through contact, induce an opposite charge in another body without contact, and create a magnetic field when electrons move. Those 5 ideas are the foundation of this entire chapter. Repulsion, attraction, conduction, induction, and electromagnetism are not separate topics. They are the basic behavior of electrical charge. Conduction is the movement of free electrons through a material. The chapter compares this to a row of dominoes or marbles in a tube. Push one end and motion shows up almost instantly at the other end. In a wire, the movement of any one electron is tiny, but the transfer of energy through the circuit happens extremely fast, effectively at the speed of light, about 297,600 kilometers per second or 186,000 miles per second. But electrons only keep moving if there is a complete path home back to the source. Break the path and movement stops. Actual electron flow is from negative to positive, but many diagrams and older electrical explanations use conventional current flow, which assumes current goes from positive to negative. You need to know both ideas because both appear in training and wiring discussions. Direct current, DC, means electron flow continues in one direction only, as with batteries. Alternating current, AC, means the direction changes back and forth. In house wiring, the current alternates 120 times per second, which comes from 60 Hz AC, reversing direction every half cycle. Induction means causing an electrical effect without direct contact. A charged balloon stuck to a wall is the classic example. The balloon does not have to transfer charge directly to the wall. It pushes or pulls charges in the wall and induces the opposite charge nearby. This same principle is used in many electrical components. Induction is one reason capacitors, transformers, and motors can work. It is a core exam idea. Electromagnetism is the 5th property. When electrons flow through a conductor, a magnetic field forms around that conductor. The direction of current determines magnetic polarity, and the amount of electron flow determines field strength. Wrap the wire into a coil and the field becomes concentrated and stronger. That is the principle behind solenoids, relays, motors, and transformers. Permanent magnets and electromagnets follow similar attraction and repulsion rules. Unlike electrical energy, magnetic energy can act across space without direct contact. But in appliance work, the two are constantly being converted back and forth. Electrical energy becomes magnetism, and magnetism becomes motion. For electricity to flow in a circuit, two conditions must be met. There must be a difference of electrical pressure, and there must be a continuous pathway from source back to source. The chapter uses water pressure and piping to explain this. Voltage is like pressure. Current is like flow. Resistance is what opposes the flow. If the switch is open or the path is broken, pressure may still be present, but no current flows. That is why a circuit can be energized and still not be operating. The human body has relatively high resistance to electrical flow, but never count on that for safety. Electricity takes the easiest path home. If your body provides that path to ground, current will move through you. Once the chapter establishes the electrical pathway, it defines the three most important electrical terms: voltage, current, and resistance. Voltage is electrical pressure, also called electromotive force, potential difference, or simply voltage. The symbol commonly used is E or V. A voltmeter measures the difference in electrical pressure between 2 points in a circuit. One point by itself does not have voltage unless it is compared to another point. That is a key exam idea. Voltage is always a difference between 2 points. Current, or amperage, is the rate of electron flow. The symbol is I, and the unit is the ampere, or amp. The chapter defines 1 coulomb as a quantity of charge, and when 1 coulomb of electrons passes a point in 1 second, the current is 1 ampere. 1 coulomb contains about 628 quadrillion electrons. That number is huge, but it matters because current is measured by the quantity of electrons moving past a point over time. Resistance is opposition to electron flow. The symbol is R and the unit is the ohm, shown by the omega symbol. The chapter states it simply: it takes 1 volt to push 1 amp through 1 ohm. Resistance is caused by the conductivity of the material, collisions between moving particles, and opposing forces such as magnetic fields or induced currents. In a properly working circuit, the load provides useful resistance and converts electrical energy into something useful such as heat, light, or motion. In a short circuit, resistance becomes very low and dangerous. Current can flow. In 120-volt building circuits, an unrestricted short can rapidly overheat wires and start a fire. The chapter directly links voltage, current, and resistance. Increase voltage and current tends to rise. Increase resistance and current tends to fall. Decrease resistance and current tends to rise. That relationship becomes Ohm's law. Even if the exact equation is covered later in the chapter, the principle is already established in these pages. Current responds to pressure and opposition. Power and work are also tied into these relationships. Current is energy in motion. The greater the current, the greater the energy delivered to the load. But that only helps if the parts are rated for it. A 120-volt lamp may glow normally at 120 volts, glow dimly at 50 volts, or burn out if too much voltage causes too much current through its resistance. In other words, components are designed for specific voltage and amperage ratings. Exceed those ratings and they can overheat, melt, or catch fire. A key safety fact: as little as 0.050 amps, 51 thousandths of an amp, can cause severe pain. Even small current can be dangerous. Voltage creates the push for current through the body, so higher voltage usually means greater shock risk. The chapter covers analog and digital meters. Depending on settings and lead placement, 1 meter can act as a voltmeter, ammeter, or ohmmeter. Common units include megohm equals 1 million, ohms equals 10 to the power of 6, kiloohm equals 1000 ohms equals 10 to the power of 3, millivolt equals 0. 0.001 volt equals 10 to the power of minus 3. Milliamp equals 0. 0.001 ampere equals 10 to the power of minus 3. Microamp equals 0. 0.000001. Ampere equals 10 to the power of -6. Important rule: start on the highest range, then work down for safety and accuracy. Analog meters require correct scale reading and multiplier use. Digital meters are easier to read, but still need correct jack and function selection. For resistance tests, power must be off. An ohmmeter uses its own battery and must never be connected to a live circuit. Open circuits read infinity or OL. Closed circuits show measurable resistance. Ohmmeters are used for continuity checks. Voltmeters connect across 2 points. Ammeters connect in series, so current passes through the meter. Ohmmeters measure resistance with power off. Series circuits have one path. Parallel circuits have multiple paths. Series parallel combines both. In series, one open component stops all current. In parallel, other branches may still operate. AC circuits also involve phase relationships. Voltage and current are not always in phase. In capacitive circuits, current can lead voltage. This helps explain motor starting and capacitor action. Capacitors can store charge. After power is removed and may deliver a severe shock. Some use bleed resistors, but safe discharge is done with a 20,000 ohm 2-watt resistor, not by shorting terminals with a screwdriver. Electricity becomes appliance action through electromagnets, solenoids, relays, motors, transformers, code, and safety. A solenoid valve uses current through a coil to create magnetism that pulls a plunger inward. When power stops, a spring returns it. Strength depends on current and number of turns, called amp turns. Low voltage or shorted coils can cause chatter, weak pull-in, or failure. Test with voltage drop across the valve or continuity with an ohmmeter. Some use thermistors for delayed action. A relay works the same way but moves contacts instead of a valve stem. A low voltage coil, often 24 volts AC, controls a higher voltage load. Larger line voltage versions are contactors. No normally open and normally closed contacts. Dirty contacts add resistance and voltage drop. Motors convert electrical energy into motion using magnetism. Split-phase motors use start and run windings separated by 45 degrees to 90 degrees. Common speeds are 1,725 and 3,450 revolutions per minute. At about 75% speed, a centrifugal switch opens the start winding. Failed switches can cause humming, overheating, or high current. Main trouble spots are bearings, windings, and switches. Multi-speed motors may have 2, 3, or 5 taps. Higher resistance tap equals lower speed. Lower resistance tap equals higher speed. Transformers work by induction. Primary is input, secondary is output. Equal turns equals 1-to-1 ratio. Fewer secondary turns equals step down. More equals step up. Example: 120 volts with 10 primary turns and 5 secondary turns gives 60 volts. Ignition transformers are step-up types, often 120 volts to 6,000 volts. Current may be around 23 milliamperes across the electrode gap. Check for cracks, corrosion, overheating, and proper voltage. Around 6,000 volts across secondary terminals or 3,000 volts to ground on grounded units is normal. Below 5,000 volts secondary or below 110 volts primary indicates trouble. Electronic igniters are lighter and more efficient than iron core transformers. About 1 pound versus 8 pounds, 45 watts versus 300 watts. They may work with 80 volts, sans input and output 8,000 to 17,500 volts, with peaks near 30,000 volts DC. Check grounding, minimum 2,000 ohms to burner, and secondary readings within 20% of each other. Replace if faulty. Control transformers are usually 120 volts, AC to 24 volts, AC step-down units. They power safer low-voltage controls. Some controls are polarity sensitive. Example readings may show 96 volts AC on one side and 144 volts AC on the other. Use correct volt-ampere rating when replacing. Power is generated stepped up to 120,000 to 220,000 volts, reduced to about 4,800 volts, then to 120/240 volts for homes. Single breaker equals 120 volts. Double pole breaker equals 240 volts. Some appliances need 20 or 30 amps. Gas appliances commonly use 15 amps on 14 AWG wire. Neutral is return path. Ground is safety path and must be bonded correctly. Follow fuel industry certificates. Regulation B149. Gas codes, accepted electrical standards, manufacturer instructions, and Ontario Electrical Code. Electrical work is limited to what is essential for appliance operation and replacing appliance components. Safety rules. De-energize before resistance tests. Never use an ohmmeter on live circuits. Treat capacitors as charged, protect meters, use lockout to tag out, respect grounding, and never let your body become the path for current.